Hi, everybody. I'm Sarah Burke-Spolaor. I'm a professor at West Virginia University, and I'm presenting this work on behalf of my student, Belinda Cheeseboro, who is a student at West Virginia University, and she's very much leading this effort, but I'm going to present it here today. So we're working with a team that involves some collaborators in InPTA, the Indian Pulsar Timing Array, and we're also working closely with Steve Taylor and Sarah Vigeland on this project. So this is a project that is a full NANOGrav search of eccentric signals in our data. So we are not just searching for one particular binary, we're going to do a full search of the sky for eccentric signals. And particularly at this point, this is very much an effort to search for eccentric signals using Enterprise, and we are currently building some code into Enterprise to do this. So let me get through this here. So I think it's always good to frame everything when we talk about astrophysics, as long as it's about binaries, to frame it in terms of galaxy evolution and merger processes. And this is really what gives us our sources, right? So we have these galaxy mergers. At some point, the binary black hole sort of gets together here in the center and eventually becomes a single black hole. And there's this issue that we suffer potentially when the binaries get to somewhere around maybe a parsec, where we don't actually know what drives the evolution of these binary black holes. So that when they enter the gravitational wave regime for us, we don't really know how long it takes them to get to that regime. We know after they enter that regime, they're fairly efficient at actually coalescing and going into to become one black hole. Before that point, we don't really know how long that earlier stage, around about a parsec, takes. Now, one other thing we don't know is what type of process actually drives them in this period. So it could be, stellar processes and some kind of refilling of the area around the black hole to then keep sending stars out and making these binary black holes, inspiral and get close to each other by releasing energy through the release of these stars. It could be some kind of gas effect that's torquing on the binary orbit in a way that drives them to evolution. It could be driven by accretion and things like that. There's many possibilities and many have been theorized. What's really interesting about this is that the types of eccentricities you expect binary black holes to have really depends on the orbital evolution process that drives this stage. So that when they enter the pulsar timing regime, they could have a big range of eccentricities depending on what is actually driving the black holes. We don't currently know what kind of eccentricities the black holes enter the pulsar timing regime with. And we don't know if the eccentricity is being driven by purely gravitational radiation at that point, or some kind of external force like gas or stars or something else. The reason we don't know that is because we don't have any examples yet of strongly evidenced binary black holes where we can actually track their orbital evolution. And of course, this is what's so exciting about pulsar timing arrays. We're going to find these and do all sorts of cool science. But why do we want to specifically search for eccentric binaries? And I kind of just said this, but we really don't know what kind of orbital evolution is driving this final parsec. Thus, we don't really know whether binary supermassive black holes are going to be eccentric. So of course, we want to search for something. We don't know where we're going to find it. Up until now, or until recently, blind searches have always been done with circular orbits, and that's a computational issue, which is just too computationally expensive to do eccentric orbits. But if we want to actually detect real, what we call continuous wave sources, and just for the people who are new to this, continuous wave sources are anything that's continuously emitting. So this is anything that's not a background, it's just one discrete source. If we want to detect those, we may just have to do eccentric sources if all of them or many of them are eccentric. And we know that some binary candidates discovered with electromagnetic emission, for instance, OJ287 is one of the most famous, where it has this double peak every 12 years, indicating maybe some kind of passage of a secondary black hole in an elliptical orbit through an accretion disk. Many of these candidates have non-zero eccentricity. So searching for those is a little bit easier because you're only targeting one object. But if we want to do a whole blind search of the sky, it is very computationally expensive, or has been. And that's the point of this talk. Because now it's really the most realistic thing to search for full eccentricity space, not just circular binaries as we've done in the past. And now it has become possible to actually do it. So I did want to frame a little bit of part of the background of just why, what eccentricity actually does to a signal for the pulsar timing array, and what it does to both our background and to the individual binary black holes. And that's sort of why it's interesting. So here I'm showing some simulations that Steve Taylor, Joe Simon, and Laura Sampson were making a couple of years ago. And they're showing here, this is the strain versus frequency curve, and looking at different, so I guess these gray bars here, these gray squiggles, which are maybe a little bit fuzzy on the screen you're seeing, those are representing individual simulations of one universe. And this is the background that they're showing. So you can see each background itself maybe is a little bit spiky. Then they've taken the average of these and shown in these red curves what the average of some number of universes are. This blue dotted line is a standard, purely gravitationally wave-driven evolution of all binary black holes, presumably in circular orbits. Well, they get definitely in circular orbits because that's how the mathematic works out. Is strain goes to frequency to the -2/3, and that's the slope in that plot. So again, if you have no interaction between the binary black hole and its environment, you're entering the pulsar timing array regime in a perfectly circular orbit, and you're pretty much following that frequency to the -2/3 law. You can see here that if you have some kind of eccentricity seated right at the beginning, you start to get this funny shape where you sort of turn over at low frequencies, and there's maybe a little bit of excess power at high frequencies. If you have very efficient evolution for various other reasons, not just eccentricity, you might even have a larger dip, and then really high eccentricities and over efficient evolution ends up with this really extreme dip down at the bottom. So one of the reasons I wanted to show this plot first is to then talk about how eccentricity drives these things. But also I wanted to point out that when you have a single binary black hole, this red line here, or any of these gray lines, the power of the gravitational wave background is made up from all of the individual contributions of power from binary black holes in those bins. So there's some population here, there's some population here, and each binary is contributing some signal to this summed curve. So you can imagine if there are fewer binaries down here, you might have a lower level of that curve. You might also have the same number of binaries, but just less power at that frequency for various reasons. And then you might have a lower curve. Okay, so let's think about that. Okay, so the very most basic way that eccentricity changes things, and part of why we need to do a more complex search than just running our power spectrum and looking for peaks in our periodicity curves of our time series. If you have a circular binary, we know that the orbit, you essentially get 2 gravitational wave cycles per orbit because there's some kind of symmetry, right? So here, one half of an orbit will give you 1 gravitational wave. The other half of the orbit will give you the other gravitational wave. Cycles, I should say, not as distinct gravitational waves, but you get 1 sinusoid there, you get 1 sinusoid here. So you can express this as, gravitational wave frequency is twice the orbital frequency. When you go for eccentric sources, you really have to use a more full expression for how that power is distributed as a function of observed frequency. So it's not a straight transition of the orbit. It actually depends on some, it comes out as harmonics of that fundamental orbital frequency. So it becomes a little bit more complicated when you talk about eccentric sources. So what happens here, of course, is that when we go back to this plot, if you're sending your signals at one, say you have a binary orbiting such that if as a circular binary, it would be emitting down here. Let's go to this plot. If it's emitting down here, if you're eccentric, you're actually having some of that power that's redistributed up to higher frequencies. So we don't get as much signal down at low frequency. There is also much more rapid evolution when you have eccentricity involved. So if you have an eccentric source, especially for highly eccentric sources, you're going to much more rapidly lose power and send your binary in to coalesce. So for the privy or DFDT term is quite high. So if you have sources, you can see this is low gravitational wave frequencies. So low frequency are generally the things that are in really, really large orbits going around really slowly. So if you have fewer sources way out at these large separations, then you will get fewer sources here. And that is partly, when you're talking about eccentricities, they're driven much more rapidly through that early stage, and you see fewer sources at those low frequencies. If you have these, gas or stars, or even just eccentric entering orbits coming in. So that is really why we get these plots turning over at low frequencies due to evolution. That slide twice. So I did want to show just an example of some eccentric signals. Here I'm showing this in one way, which is showing separately the Earth term and the pulsar term. So Earth term is on the left, pulsar term is on the right, and this is the power as a function of time. So you can see that the pulsar term and Earth terms, are really quite different, and really much more extremely different. And you can see how rapid this evolution is at something like an eccentricity of 0.8. So the pulsar term, remember, is, I always get this wrong, is the older time. So pulsar term, let's see, Earth term lags pulsar term. I'm always going to say this wrong, but so the pulsar term is you're seeing the source at an earlier orbital frequency when it's very far apart. So you can see the slow orbital evolution of that gravitational wave signal. The Earth term, we're seeing it, directly from the source. So you get this really, really much more high frequency signal. You can see down at this lower eccentricity thing, you get much less rapid evolution, and this source really looks at least sort of circular. It's relatively sinusoidal. So this just highlights that you have very, very different Earth and pulsar terms, and you get that rapid evolution. So here I wanted to show a plot from the work by our InPTA collaborators. This is a paper led by Abhimanyu Sushobanan. Sorry, I spelled his name wrong on this slide. Look at the first slide for the correct spelling. And here we're showing a slightly different plot. So these are residuals calculated, again, as a function of just time referenced from some arbitrary position. And these are, again, different eccentricities. Here, though, for the two different lines in each plot, we're showing two pulsars spaced at slightly different, well, the same pulsar, but just spaced at a slightly different position, distance from Earth. And on the left is a binary at 1.5 year orbit, and on the right is a binary at 5 years orbit. So I think this is a nice visual. So indicating that first, yeah, evolution is still really rapid, but there's a little bit less difference on the right here between these two distances, because this is a little bit of a more widely separated binary. This one, so sorry, give me one sec. Hi there, sorry, I thought I heard somebody about to come in. So the one on the right, I think I was saying, was a widely separated binary. You get a fairly slow evolution, or at least a slower evolution. On the left, you have one that's more rapidly evolving. And you could see that even just a little bit of difference in this pulsar distance comes in a fairly large difference for all eccentricities in the pulsar terms influence on these final residual signals. All right, so I wanted to just say one quick thing on why we don't already search for eccentricities just by standard. And the real problem comes down to the fact that when you're trying to search for that evolution, you have to account for the pulsar term, and you have to account for the Earth term. If it's a circular binary, you're getting one sinusoid, and you're changing that sinusoid into a higher frequency sinusoid. With eccentricity, you saw here that, let's see if I can get this earlier. You saw here that these eccentric signals can be quite complex, and they can change in not really, definitely nonlinear ways as a function of time. And here is the kind of root of the problem. This is the orbital evolution expressed for an eccentric binary supermassive black hole. These are the leading orbital terms showing the semi-major axis as a function of time right there, and the eccentricity as a function of time there. So these are coupled nonlinear differential equations. And to actually compute these in real time with computers really requires serious computing power. So not many people have done this. And here I'm showing a call out to this paper spelled correctly this time. And there's the archive posting if you guys want to take a look at it. So what these guys have gone off and done was something amazing and made a semi-analytic and fully analytic frameworks for calculating evolving signals for eccentric signals, and actually how to generate residuals for eccentric sources out to really a few post-Newtonian orders. And it really speeds up the processing by a lot, something like a factor of 100 compared to normal searches. And here, again, we're showing, here's just a measure of the gravitational wave strength as a function of time, much like the plots we've just been showing. And this is just a demonstration between a full, a numerical semi-analytic mode for this, which is more accurate, versus their analytic approximation to this. And you could see that they really match up pretty well, particularly at low eccentricities. At higher eccentricities, it's not quite as accurate, but still doing very, very well and suitable for searching. Now, what we are trying to do is take the framework that they've coded up here and actually build it into Enterprise. And there's been a lot of work going on to make this happen. So what we're trying to do is build this just module thing. We know that Enterprise is meant to be sort of a plug and play kind of thing as much as possible. So we're trying to meld the algorithm set down by Steve and Abhimanyu and collaborators. We're kind of trying to blend that into Enterprise. You all know that this is a pulsar timing analysis code, of course, standard use by NANOGrav in our collaboration for all of our searches these days. So this work is well underway. We have actually done this first point now. We've built this GWX code into Enterprise. It's all coded up. And we are now working on just testing this code and making sure it actually finds what we expect it to find. I'll show a plot of that in a moment. Our ultimate goal of this, and really we're building up to this next step now, we're going to try a blind search of one target and one sky position. And the one we're going to target first is likely going to be the source 3C66b that Caitlin Witt has worked on in the recent past. There was a paper in the past year about this, searching for that source in just circular orbit assumption. So we're going to try to search for it in eccentric, a full eccentricity search. We're then going to try to extend this to a full sky search of the 12.5-year data. So here's just an example of what we've been doing presently. And I'm showing 4 different histograms here that are just demonstrating the tests we're doing to examine the interaction between the GW eccentricity code and Enterprise by just injecting a simulated eccentric signal into a simulated pulsar timing array data set. And I think this has 10 pulsars in it with constant noise, ideal parameters all around. And we're focusing on detecting these 4 parameters. So this is eccentricity, or this is the initial eccentricity, when you first inject that binary. I've got to say, I don't know what that is. This is the mass ratio, and this is the chirp mass. I can't remember what F4B stands for. Ask Belinda if you see her. And you can see that this black line is actually the injected line, the injected signal value. You can see that we're not really spot on for these, so we're just making sure all of our parameters are lined up and cross-checking the codes. It is possible we are running into some issue where there are actual covariances between some of the eccentric parameters and some of the pulsar parameters that are leading our algorithm astray when we're actually trying to recover the actual injected parameters, but we're still running some tests on this. So I'm going to end there, but I think I want to give you some takeaways. So first, eccentric searches are now searchable, and we're hoping to continue doing this once we've gotten a full pipeline to actually run on the 12.5-year data. This will be something we hope to do in the future in NANOGrav as a systematic standard analysis. Our search is underway. We're not yet searching the full data set, but that will be soon to follow from our present work. And just to wrap this back around to the science, a discovery of an eccentric signal first would, of course, be very exciting. It'll be the first detection of any binary eccentricity for supermassive binary black holes. And this would also really help us inform about this, last final parsec stage of inspiral. And it will hopefully then help us interpret our gravitational wave background signal, which presumably we would have detected by the time we actually get an eccentric signal. And thanks for listening. Bye for now.